Okay, looks like everyone's back. Okay, so we're so each of these at our present value, we calculate these branch metrics, right? That are reflective of this immediate preceding or the current step or transition that gets us to the current state. All right. But we're also keeping track of the path metrics for each of these possible paths going through this trellis. And we're going to do that over some number of steps. And we're going to keep track of each of these possible paths and keep adding the branch metric over and over again as we get more input bits into the system or message or more parity bits, right? So one more back. So we calculate this branch metric at each timestamp, and then we add it to the path metric. Okay, or so these are the summed values for each path through the trellis. And we're going to perform that calculation for each possible state. We're going to retain the best path into each well, each state node. Sorry, that's a bit of a typo there. We're going to retain this best path, and we're going to call that the survivor. And we're going to do that based upon a minimum distance, calculated distance. So if we look out here as we get into this trellis here a little bit, we see that for this code rate 2 system, well, for a system that's binary, has binary inputs, each of these states are going to have two possible paths that could get us there, right? And so in this state, we could have this path or this path. In this state, we could have this transition or that transition. So we're going to calculate the branch metrics for each of these, add those to the path metrics, and retain one of those as we go through the system. You can imagine that the number of possible paths otherwise grows very problematically. So as you go forward in time, and you don't want to keep track of every single potential one. So at each state, we prune it. Each time step, we prune it so that we're only retaining one survivor. So it's a term we use in this algorithm. So we calculate path metrics through the trellis for the received message. We do this using this add, compare, select at each timestamp, time step. So we're adding that path metric, the branch metric to the path metric. Then we compare the two possible ones coming in, and we select one of them, the best one. Generally, the way problems normally cast, we choose the smaller of the path metrics, but we add it first, right? So we're not just looking at the branch, we're looking at how we got there. And then ultimately we get to the end, we'll trace back the path that has the minimum path metric. In other words, it matches the received bits with the expected bits the best, right? It has a minimum distance for each of those. And so that's how we're calculating that path metric. And then we'll look up the message bits corresponding to the state transitions that we use to calculate all this stuff. All right, so this is going to be hopefully clearer here in a minute. We then now have the message bits, and we just need to reorder them instead of last to first, we'll switch them around and go first to last. The system algorithm is somewhat memory and compute intensive, but for smaller constraint links, it's very advantageous. It can be easily implemented in FPGA logic or software, much like the Fourier transform and other ubiquitous type of algorithms that we deal with in engineering, electrical engineering in particular. We used to have to derive all these things and create our own logic, but now there's canned solutions to these. So if you're designing this, you can go to Altera or Xilinx and just download some already pre-built core that you can implement in your FPGA that would do this algorithm. So let's go through an example now. And so we're going to use the same generator pair of generators that we looked at before, the 111 and the 101. So and this is basically going to be the same trellis. So this trellis is describing the generation of a code, and now we're going to try to fit the received bits into what we expect the thing to have based upon the code structure that's implemented in this trellis. Okay, so we're going to have assume that we have received bits. Now these are parity bits, right? So we're going to have 2 for every message bit that we're trying to decode, right? So we're going to have 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, and 0, 0. And this is increasing in time as we go to the right. So this we first receive a 0 and then receive a 1 and then the 1 and 0. So I know sometimes we flip-flop back and forth between those orders. So this describes our different states of the system. And so if we now want to start calculating our branch metrics, here we have received bits of 0, 1. For this transition, we would have expected to have parity bits that are 0, 0 if the message bit had been a 1 from this initial state. If the message bit was 1, then we should have gotten parity bits of 1, 1. So right away we see that, wow, there must have been an error there, because that's not a legal set of output bits. Okay, so we can start to suspect that there might be an error in our system. But so let's calculate our branch metrics. 0, the distance between 0 and 0 is 0, plus the distance between 1 and 0 is 1. You add those 2 up, and that's a 1, right? So at the beginning, since we're starting in this state 0, 0, we don't have another possible transition entering into this state, so we only have to calculate that one. Likewise, here on this state, we have 0, 1, that's a 1, 1 and 1, well, those are equal, so it's just 1. The distance between the received bits and the expected parity bits is just 1. That would be such that it would transition to this state 0, 1. Okay, so now we can do the next one, and here we have 1, 0. That would be our branch metric here would be 1, but our path metric here is 1, so our total path is 2. Here we've got a branch metric of 1 plus 1 for 2. Here we have a branch metric of 0. Hey, that was good. 0 plus 1 is 1. And here we have a path metric of 2. Wow, both those digits are different, right? So the branch metric is 2 plus 1 gives us 3. Okay, note that we're using hard decisions and we're calculating the distance between the receive bits and what would have been the resulting output bits based upon the message bit and the state that we're in. But we started in state 0 there. Okay, so it's been simple up to now, but might get a little more complicated, but we're just applying the same rule each time. So it gets messy, but it's still, if you break it down on each time step, it's pretty straightforward. So let's look at this node right here. Well, we now receive 1, 1, and for this transition to get us to this state, we would have expected to have 0, 0. So the branch metric is 2 plus the 2 to begin with for our path metric. Okay. Now, in this case, we've evolved far enough into the trellis that now we have alternate paths coming in, right? So we calculate this branch metric. That is a 1, 1. So that branch metric is 0. Okay, but we started with 1 for that path metric. So we have a 4 compared to a 1. Well, obviously that 1 is the minimum, right? So it has a minimum distance from what we expect. So we X out this one, this transition, and we call this one the survivor. Okay. So this is going to survive and this one's going to die. So, all right, let's look at this node. Now we have a branch. Well, if we look at this, okay, so if we have a 1, 1, 1, that's a 0 for the branch metric, but we have a 2 for that path metric. And then this one, we would expect it 0, 0. We got 1, 1. So that branch metric is 2 plus the path metric is 1. The minimum here is 2. So we call this one the surviving path and we X out that. So then we continue through this process and we just keep repeating here, right? So I think I cut off the transition, but it should be the same as this. So you'll note that these numbers, these input bits and expected output parity bits just kind of replicate for each transition as you go along. Does get a little messy sometimes though. So but this one should be the same as this one. So a 0/1, 0, that would be a branch metric of 1. We started with 2, so that's going to be summed to 3. We compare that with this one. So 1, 1, 1 versus 0, 1, that's a branch metric of 1 plus that 3. So we're going to retain the value 3 here. Okay, and that corresponds to this survivor, and this one's going to be dropped. And finally, here we have a branch metric of 1 for this one, and previous path metric of 2 versus a branch metric of 1 for this value compared to that, plus the path metric of 3. So this is going to be an overall metric. The minimum one is going to be 3. These all become your new path metrics. Okay, and so here we retain that one. Okay, so now you just copy it over and you look at the next timestamp, right? So now, as I said, those values we just calculated become the new path metric. So you just update your path metric as you go along and you repeat the process. At this point, it's not any more complicated than the previous one. So you can go through and we'll see here. We got 1 0. We expected 0 0. So that's a branch metric of 1 plus the existing path metric is 1. So we have those for that branch, that state transition. And then we calculate it for this other available transition. 1 0 versus 1 1 is going to be a branch metric of 1. We look up the path metric, that's 3. Okay, so we have 2 compared to 4. So obviously 2 is smaller. So we update the trellis accordingly. So we go through this for each timestamp. We go through and examine each state, and we calculate the branch metric for each possible transition into that state. We add that branch metric to the path metric, and then we choose the smaller of them, right? The one that basically is matching better, because again, we're doing this on a distance basis. We're saying that we want to minimize the distance between what we received and what we expected to receive, right? So, and then we update and move to the next one. So here we go to the next one, and we repeat that process. You can go through that and verify that yourself. And now we get to the end, and we look at these, and so here we have received 0 0, and we we look at this branch, that would be a 0 0, and so our branch metric is 0, matches perfectly. Our path metric was 2. So conversely, this one, well, our branch metric is 2, added to that one. Actually, it should be a 3, shouldn't it? Or I copied over something wrong there. But regardless, the 2 is going to be the smaller of the 2 branches. So we retain that one and we X out that one, and go through here also and repeat that. So now we have a 4 versus 3. So we retain the 3. 3 versus 4, we retain the 3 and X out the other one. And again, 3 versus 4. So we have this transition as the survivor, and this one as the one we cancel out. Now we look at all these, and we identify the smallest of all of those, right? So this last set of numbers we've calculated is our cumulative path metric for each potential path through the trellis. And so this includes the effects of all of these different time steps. And so our path metric here being 2, that's smaller than these others. That means that this path that brought us to this node here, this state here, really had the fewest misses or the fewest errors in the process. So now we can step back, or what we call trace back, and look at try to reconstruct this path. So now we're at this time step. That's presumably the end of this block of data that we expected to get, and we're choosing this as the best result state. So we're assuming we're in this state. Now we look at a history of what we've done, and we trace back and say that, okay, well, that survivor path led us back to this state, and this survivor path led us back to that state, and this one to this state. All right, so that looks kind of boring, but here we're at this point. Our survivor path takes us down to this state down here, and so on and so on until we get back to the beginning. Now I've already bolded, increase the weight on these lines here, so to make it obvious. But yeah, you get to the end, and now you have to construct this path and figure out how did you get to here from there, right? So this is called the traceback process. Not terribly difficult, but you can imagine that you've got to keep track of this in memory, right? And so now you've done that based upon these output bits that expected and taking you to different states that are associated with that. Now you can look up the bits, the input bits, the message bits that resulted in all of those state transitions, right? So now you read off this 1, 0, 0, 0, 0 type of thing. So, yeah, in words, if we flush the system by ending our message with k minus 1 0, so we fill that memory register up with zeros, then we should end up at state 0, and we can start our trace back from there. So if we look at that, that's the set of parity bits going from the right-hand side, or the last time step, previous one, previous to that, and so on till we get back to the beginning. These are the those are the states that we transitioned. Okay, and then we look up the message bits while reordering. Okay, so again, you look up the bits, so that's a 1, 0, 0, 0, 0. So we're reordering by starting from this point and going to there, whereas our traceback started from here and went back in time, right? So now we're going forward in time and looking up those bits each time. So that's our message that we, in a maximum likelihood sense, expected to have been sent. Okay, again, maximum likelihood, when we're using that algorithm, we're making the assumption that our input bits are equal probable. If they're not, this algorithm needs to be modified, or you need to use a different algorithm altogether. And of course, people have done that. So so now we can look, and we can note that there are errors in the first and seventh receive bits, right? So so this first bit, we see an error here. That first bit, this one was 1 0 1 0. This one's 1 1 and 1 1. This one's 0 0, but we received 1 0, right? So that's an error there, and that's an error there. So we were able to correct both of those, right, by looking at not just a snapshot in time, but the way that the system could legally transition from state to state. Right? Okay, so in some cases, we might have a continuous stream of data. And in fact, that's often the case, right? So we can't really wait until all the data is received before selecting the last survivor. Wow, how did I spell that so bad? Survivor. Survivor. And perform the traceback, because we would be faced with an excessive delay. It might not be the end of the world. These convolutional codes were developed really kind of came into their own, I should say, when NASA was first sending space probes to other planets, right? Back in the late 60s and early 70s in particular, um, these convolutional codes were employed there. And now you're taking some picture at the reaches of our galaxy, solar system. We're sending these things to Mars and Venus and that type of thing. And yeah, sure, those are neighboring planets, but they're still pretty far away. Those satellites only have like 20 watts of transmission power. That's smaller than a base station, a modern base station, or maybe not far off from a modern base station. And that you don't have to go very far from the base station before you start having signal problems, right? So how in the world are we going to get that data back from these far planets? Well, one is we can use huge antennas on the Earth to try to get as much antenna gain as possible to intersect as much of that electromagnetic signal coming from the satellite in this high gain antenna, but we still are dealing with an almost seemingly insurmountable problem. Well, we use error control coding, and in particular these convolutional codes, and there you can imagine, well, you could just download all of the coded bits and for some picture, right, where each set of information bits are going to be related to the pixels of these imagers, right? And then it's each pixel's represented. I think in the beginning it was like a 6-bit type number, and so each of those bits then gets converted into a parity bit through this convolutional coding. And now you can download them all and then do all this decoding in a post-processing situation. But there's a lot of other situations typical in two-way communications where we want to be able to not have this excessive delay. So we want to be able to find these ideal paths and do the trace back and the extraction of the message bits kind of on the fly, right? So as it turns out, yeah, if you kind of wait, do this over a period of time steps, that's somewhat a function of the constraint length. So maybe we do 7 timestamps and time steps and then do a trace back. We're probably pretty well converged, and so that's a pretty common type technique. You don't always have to wait till 0 till the end of your message if the message is kind of a continuous block and we don't return to some value of 0000 type of thing to flush that out. All right, so our storage and computational complexity is proportional to 2 to the k minus 1. So the more memory you have, the more states you've got to keep track of, the more paths you need to keep track of. So, but it's still, pretty advantageous and practical for constraint lengths less than 10. For things greater than that, we use some other techniques. We don't have the time in this course to look at those, but sequential coding is a potential solution for that. So we mentioned soft decisions earlier. So instead of calculating the Hamming distance from the bits, we use the voltages from the integrator sampler of the receiver and compare that to the expected voltages at each step and state. So we can normalize that to maybe 0 to 1 volts or whatever. You've got to have some sort of process to do that. And then instead of subtracting bit values, you're subtracting the voltages and looking at the absolute values of those, I think. So and now you're retaining additional information. Obviously you're not doing 1-bit math. Let's step back and say that a modulo 2 addition step for a single bit, if you're doing this on a bit by bit basis, is simply an exclusive OR gate. Right. So let's think through that truth table, right? So for an exclusive OR gate, 0, 0 produces 0 output. 0, 1 produces a 1 output. A 1, 0 produces a 1 output. But a 1, 1, because it's an exclusive OR, a 1 on each of its 2 inputs is going to produce a 0. So you can calculate the Hamming distance using for each bit using a single exclusive OR gate. So if you're doing voltages, well, you need to represent those voltages in some number of bits. Maybe you still use integer type math as opposed to floating point, but it's still going to take a little bit more computation to do that. So there's trade-offs, but soft decision definitely is going to use more information in its decision process. All right, so other codes. Of course, this has been an intense field of study for researchers and grad students trying to get their PhDs. Like I say, it's you just come up with a better code, right? And so one thing to note is that the bits are often permutated after coding according to a specific pattern to help deal with burst errors. So when we talked about that interleaving process way back here, we showed this, right? P0, P1, P0, P1. So we can oftentimes we will permutate or reorder these things to kind of get maybe this P01 away from this P11 and get it into a different location, or even just this 0, 1, and 2 of P0 into a different time location. And therefore, if you do have a burst error that wipes out a couple of or a few bits in a row, because we've reordered them, perhaps some of those bits will survive. And at the receiver, we restore the order and then do that decoding process. So that's what we mean by permutation there. Sometimes we use both block and convolutional codes. So we'll code it once using let's say the block, and then we will run that resulting code word into our convolutional coder, and we kind of get the best of both worlds. We tend to keep increasing our effective code rate when we do that. Sometimes then we puncture the code. You may hear this term. I'm not going to hold you accountable for that because I don't have that written down here, but you can then just throw away certain of those redundant bits, again, according to a known a priori pattern, puncturing pattern. And so even though our code rate's increasing, if we just puncture or throw away some of those codes, then we kind of regain some of that rate. And obviously we're throwing away information, but it turns out that sometimes that's a beneficial step. So, so the codes we talked about are kind of standard and fundamental, but the kind of latest state-of-the-art codes that actually are approaching that Shannon limit, that capacity that we calculate using Shannon's capacity theorem. You know, coding is the way we get there, right? We approach that limit, and so some of those current codes are turbo, low density purity check, or LDPC codes, and polar codes. These are iteratively solved using belief propagation and soft input and output, and they're used in 5G and other recent standards. So perfect timing. I've uploaded this document, I think, to the Moodle, and there's might be a few other things that I will put up there. There's this one actually is someone's lecture, I think, from the University of Texas, and it in the last page of their lecture notes, they talk about some of the structures, data structures you would need either in an FPGA or in a like a C code type implementation of this in order to do all this calculations, but then need traceback and the bit extraction and stuff. So, all right, have a good weekend, and hopefully I'll see you on Tuesday if my drive goes well to New York. So, all right.
Travel safe, Professor. You up?